All right. Hey everybody, welcome back. We are going to continue looking at parametrized surfaces today. And in particular, we are going to begin looking at tangent vectors to parametrized surfaces. Now this is something that we need to rigorously define here in a moment, but remember back when we were looking at parametrized curves, one of the very first things that we looked at were our tangent vectors, or vectors that lay tangent to the curve. We ended up being able to find these by taking derivatives of our parameterization x, and in general, these led to the definition of our unit tangent vector, measurements of curvature, and really every sort of piece of differential geometry that we saw followed from this idea of being able to find tangent vectors. And so it stands to reason that this is a good place to start with surfaces as well. Now, before we start taking derivatives of our parameterizations, we're going to define our tangent vectors in a slightly, in my mind, sort of stealthier way, sort of a nice slick way here. And so let's start with a schematic here, right? So here is a parameterized surface, right? Or at least a coordinate patch of a parameterized surface. So we could imagine that we have a surface S here. And in particular, this is a piece of that parameterized surface, right? This is that coordinate patch that we spoke of last time. Let's say here's the parameterization of the coordinate patch. And here's a point on the surface, P, which we want to look at and try to find tangent vectors of. And those would be vectors that are tangent to the surface. Now, like I said, our gut might tell us to start trying to take the derivatives of x, right? And to maybe take derivatives with respect to u or with respect to v. But before we do that, there's a slicker way to define a tangent vector here. And that's going to be as follows. I'm going to look at a parameterized curve that lies entirely in the surface S, and then just refer to my definitions of parameterized curves and their tangent vectors to make my argument for me. So specifically, here's my surface S, here's my point P. Let's take a parameterized curve, right? So maybe this is my parameterized curve here. And I want to point out that if I calculate any vectors that are tangent to the parameterized curve, as long as the curve lies entirely within the surface, any vector tangent to the curve will also necessarily be tangent to the surface as well. And in particular, if this is my curve, and I then go and calculate the tangent vector to my curve at the point P, that vector will be tangent to our surface. No additional work necessary. And so maybe to make this a little more rigorous, what I would want to do is define a parameterized curve. And to avoid any confusion with using the letter x, I will more often than not start calling my parameterized curves gamma. Now, that's sort of the classic definition for them. So if I define a parameterized curve gamma, right, and gamma will take an interval. So here's my interval up to the endpoints, and then gamma will map this interval onto a curve, and specifically the curve on the surface here. Then I can find a curve for which I define maybe this point in time is 0, and I define gamma of 0 to equal p. Right? And so if I find a parameterized curve gamma for which gamma of 0 equals p, then I can calculate this tangent vector just by calculating gamma prime of 0. So gamma prime of 0 will equal some vector v. This is a drawing of v right here. And then the claim is that since v is tangent to the curve, and the curve lies within the surface, this will also be tangent to the surface. And so this will be sort of our starting point for finding tangent vectors to surfaces. And we can summarize this as follows. All right, so if we take a parameterized surface S and take P to be an element of S, then we define a vector v to be a tangent vector. I should really underline that. So a vector v is a tangent vector to S at P if there exists this curve gamma that we discussed such that gamma lies entirely in S and satisfies these two properties. Gamma of 0 is equal to p, so at time 0, we are at the point p in question, and then gamma prime of 0 is equal to v, so the tangent vector to the curve is equal to v. If we can find such a gamma, and if these two things are satisfied, then v will be a tangent vector to the surface. I think that's kind of interesting because part of this definition says in order for us to define this vector to be a tangent vector to the surface, what we really need to do is find a parametrized curve, even if, say, this gamma isn't necessarily given to us ahead of time. All right. Okay, so in addition to finding individual vectors, which are tangent vectors by the above definition, we are also interested in finding the set of all tangent vectors. Right? So looking at all of the possible vectors, determining which are tangent vectors and which aren't, and then looking at the set of all tangent vectors and seeing what shape that set has. Right? So we will call the set of all tangent vectors to the surface S at the point P, we will call this the tangent space at P, and it will be denoted using this notation here, T sub P of S. And I could read this out loud as the tangent space to the surface S at the point P. Now, like we said, a big question of ours will be, what does this space, TPS, actually look like? Right? And so let's go back up to this picture here. Right? Well, if I look at this, right, I have this particular vector. It lies tangent to the surface. And the very first thing that I want to claim is that if I found this vector v that lies tangent to the surface, and so it's a tangent vector, then any scalar multiple of v will also be a tangent vector, right? And I can do this by taking the exact same curve gamma and then reparametrizing it, specifically speeding it up or slowing it down to get a scalar multiple of this velocity vector, right? So again, if I took the exact same locus, but I traced it out at twice the speed, so my parameterization goes twice as fast, right? And if I went twice as fast, I'd get a vector v at this point that is twice as long. And if I went 3 times as fast, I'd get it 3 times as long. And for any real number, I can scale that vector out by reparametrizing with an appropriate speed. And if I want to go in the reverse orientation, so starting at this point and then tracing back this way, I would get the vectors going in the opposite direction too. So once I have a single vector v that is a tangent vector, every other parallel vector will also be a tangent vector, right? And so I'll get this entire line that is a part of, I should say, line of vectors that is a part of my tangent space. Now what that means is that my tangent space will really be the union of a collection of lines, right? Because every single vector will incorporate this entire line of vectors. And so that gives me a little bit of a sense of what my tangent space will look like. But in this particular example, I want to claim that it won't just be a single line or a small collection of lines. It will be a collection of lines that really give us an entire plane. Right? And we'll end up with a tangent plane, or the plane that sits tangent to the surface at this point. And we can sort of see that in this picture here, which I'll illustrate to try to make that more clear. First, what I just said, I'm sort of stating up here as a fact. If a vector is in TPS, then any scalar multiple of that vector is also in TPS. I apologize, that should be an S. And so in this picture, right, we not only had this vector, which was a tangent vector, and then every scalar multiple of it going in both directions, but we could also find other vectors that maybe, if we think of this as a graph with a little hill here, that approach the hill from a slightly different angle. And so I could come up with a curve. Maybe I'll choose a different color here. I could come up with a curve that approaches from this side, and that would give me a vector pointing in this direction, as well as all scalar multiples of that vector, right? And I could come up with other vectors that point in other directions, and ultimately, I would end up describing every single point in this plane by finding an appropriate curve gamma. And so in this case, we would get a tangent plane. Now, of course, this is a little hand-wavy. I haven't really done any rigorous mathematics here, but it feels intuitively right, especially when you consider we were thinking about curves, and these tangent vectors along curves ultimately define tangent lines. It feels a little bit right, or makes a little bit of sense intuitively, to think that our higher dimensional objects, now surfaces, will have higher dimensional tangent spaces, not just lines, but perhaps planes. Before we get too far afield, though, or before we let our intuition take us too far, I want to caution you that it won't always result in a tangent plane. The tangent space will often be a plane, but it might not be, and it's important for us to try to discuss this. Here is an example of a surface with a weird point, right? This surface looks like two different cones meeting at a vertex point here, and the point that I'm interested in is that vertex point. Now, if I drew a curve gamma here, right, any curve gamma would probably have to go through that point and then sort of pass from one cone to the other in order to do so smoothly. And so when I go to take the derivative of this curve gamma, what I will get here is a tangent vector that points down along the cone, right? And if I chose a different curve, right, so maybe I checked this curve, and I come from the top here, right, and I'm coming down here, what I would get when I go to calculate the tangent vector is another vector that points just directly down the cone. So in fact, all of the vectors that I'm calculating here are coinciding with the sides of the cone, sort of pointing down the sides of the cone. And in the end, the set of all such points, my TPS in this case, will actually completely coincide with the cone, with all of these vectors pointing down the cone, or if my curve starts down here and winds up, then it'll be pointing up here along the upper cone. And so here's an example where we don't get a tangent plane, we actually get a tangent cone that looks like a traditional cone. So in this case, we actually end up with a surface. So here we get that TPS is not a plane. And so we could ask ourselves, I guess, is this likely to happen? Like, this seems sort of like a weird example. And in particular, the point that we examined was a weird point, right? It was this weird vertex point of this cone. So is that a problem, right? I mean, this point looked a little bit more smooth, a little bit more normal, a little bit more regular, perhaps. And it had a tangent space that was a plane. And so what we'll see going forward is that oftentimes our surfaces that are nice in a reasonable way will have planes as their tangent space, while these more bizarre tangent spaces that are non-planar cones will be surfaces that are degenerate in some way. And next time we'll see a way to calculate whether or not our tangent space will in fact be a plane.